Yes, in this video we are going to solve this problem LPP with three constraints, right? So the first step is to express the problem in the standard form. The objective function should be of maximization type. It is so here. So maximize z is equal to 4x1 plus 5x2. Constraint should be of equations in the standard form, and before that you should ensure that the requirement vector should contain only positive elements. x1 plus 2x2, some quantity should be added to the left so that it becomes an equation. That quantity is an unknown quantity called as slack variable plus s1 equal to 100, and for the second constraint you are adding a slack quantity s2, and in the third constraint you are adding a slack variable s3, and these three variables are assigned zero costs in the objective function. Now I have written the cost vector here and the coefficient matrix. The coefficient of x1 is 1, x2 is 2, s1 is 1, s2 and s3 are 0. After writing this coefficient matrix, the variables for the initial basis are identified using the unit submatrix. So the column 1, 0, 0 corresponds to the first variable, and this column gives you the second variable, 0, 0, 1 the third variable. So after doing that, go to the first iteration, our initial iteration. The basic variables are S1, S2 and S3 in that order, right? And then write the coefficient matrix here. The requirement vector, let us compute Zj as the sum of the product of the elements in the cost vector and the coefficient matrix. 0, 0, 0. So Zj 0 everywhere. Now Zj minus Cj, the net evaluation, 0 minus 4 is minus 4, 0 minus 5 is minus 5, 0 minus 0, 0 minus 0, 0 minus 0. The most negative net evaluation should be selected. So we understand x2 enters the basis. Compute the ratio. While computing the ratio, remember, you should compute the ratio only when the value aij is positive. When it is negative, you are not supposed to compute. So 100 by 2 is 50, 100 by 1 is 100, 10 by 1 is 10. The minimum of these ratios is 10. So S3 leaves the basis. Right? Now let us do the calculation for the next iteration. First row is not a key row. So you should compute a constant k. For computing k, the formula is the value in the key column 2 divided by the key number 1. So 2. Old value minus corresponding value in the key row into constant. So 1 minus 2 is minus 1. Old value minus corresponding value in the key row into constant. Right? Old value minus corresponding value in the key row is 0. Okay? Into constant. Old value 0 minus corresponding value in the key row is 0 into constant. Then old value is 0 minus corresponding value in the key row into constant. Then 100 minus corresponding value in the key row into constant. So 100 minus 20 is 80. This is the calculation for the first row. Now go to the second row. Right? Second row is also not a key row. So compute k is equal to the value in the key column divided by key number. See this value by 1. It is 1. Now old value minus corresponding value in the key row into constant. 2 minus 1 is 1. Then 1 minus 1 into constant 0. 0 minus 0 into constant 0. 1 minus 0 into constant 1. 0 minus 1 into constant minus 1. 100 minus 10 into constant 90. Fine. Now for the third row is a key row. So divide all elements by the key element. If you divide all these elements by the key number 1, you have 1, 1, 0, 0, 1, 10. Fine. So with these values, let us frame the table for the next iteration. So second iteration. The variables are S1, S2. We have decided that X2 is going to enter the basis, and to that effect S3 leaves the basis. So you have X2 here. For X2 the cost is 5. Right? Now we have done the calculation. You just take these values: minus 1, 0, 1, 0, minus 2, 80. Minus 1, 0, 1, 0, minus 2, 80. And for the second row, 1, 0, 0, 1, minus 1, 90. And for the third row, 1, 1, 0, 0, 1, 10. Now compute Zj. See here the product is 0. When you multiply these two, the product is 0. Here it is 5. Right? 0 plus 0 plus 5. 0 plus 0 plus 0, 0, 5, 50. Now compute Zj minus Cj. 5 minus 4 is 1, 5 minus 5 is 0. So all Zj minus Cj is greater than or equal to 0 for all j. The optimality condition is reached. So the solution is optimum. You are supposed to give the values for the decision variables x1, x2, and you are supposed to write the maximum value of z. x1 is not in the basis here, so it is 0. x2, the value is 10, and the maximum value of z is 50. Fine. Thank you.